If G is equal to GCD of B and C, Theorem 1. Let's start the proof of Theorem 1.3. The statement of Theorem 1.3 says if G is equal to GCD of B and C, then there exist integers x0 and y0 belongs to set of integers such that G is equal to Bx0 plus Cy0. Let's start the proof of this theorem. Consider consider the linear combination consider the linear combination of B and C such that Bx plus Cy, where x and y belongs to set of integers. Here the value of this set. Here here the value of these sets like bx plus cy, the value of these sets bx plus cy can be positive, negative, and 0. 0 when x and y both are 0. Now choose x naught and y naught so that bx naught plus cy naught is the choose x naught and y naught so that bx naught plus cy naught is the least positive integer L in the set. In the set, I mean this set bx plus cy. Thus, L is equal to bx naught plus cy naught. Bx naught plus cy naught. Now we have to show L divides. Now we have to show. Now our claim is b sorry L divides B and L divides C. L divides B and L divides C. Suppose on contradiction. Suppose L does not divides B. Then by theorem, then by theorem division, then by theorem division algorithm, there exist Q and R belongs to Z such that B is equal to LQ plus R, where R lies between 0 is less than R is less than L, hence inequalities. This implies R is equal to B minus LQ. We put the value of L. Is equal to Bx naught plus Cy naught into Q. Now take the common values. R is equal to B into 1 minus x naught Q plus C into minus y cube. y cube. Now r is equal to this implies this implies r belongs to bx plus cy, means the r belongs to these sets bx plus cy, because this is integers and this is also integers, so r is in the form of bx plus cy. This implies r belongs to these sets bx plus cy. Since by division algorithm we take the above condition, 0 is less than r is less than l, so and l all r and l both belongs to these sets bx plus cy, and take the take l is the least positive integer, here here choose here b is the least positive integer. L means L is the least positive integers in these sets bx naught plus cy naught, and R also belongs to these sets bx plus cy, and R is also positive integer because 0 is less than R. So this is the contradiction. This is the contradiction. This is the this is the contradiction. So this hence our assumption is wrong. Hence our assumption, a supposition is wrong. This implies L divides B. Similarly, we can show L divides C. Now let us assume, it is given that G is equal to GCD of B and C. Given that GCD of B and C is equal to G, this implies G divides B and G divides C. Then by the definition, there exists X naught, there exists, we take M and N belongs to set of integers such that B is equal to Gm and C is equal to Gn, and it is also, and also we take L is equal to B x naught plus C y naught. Now we put the values of B and C from here. B is equal to Gm and C is equal to Gm. Then L becomes Gm x naught plus Gn y naught. Mm, This implies L is equal to G into M x naught plus N y naught. This by the definition of division, divisibility, G divides L. G divides L. And we know in the theorem, and we have already proved that in theorem 1.1 part 5th, if G and L both are positive and G divides L, and G divides by theorem 1.1 का fifth part, we have already saw that if G and L both are positive and G divides L, this implies G is less than or equal to L. But G is less than L can't possible. Can't possible as G is the GCD of G is GCD of B and C. This implies G is equal to L is equal to B x naught plus C y naught. Hence, our proof is going to be proved, completely proved. Now we go to the next theorem, theorem number 1.5. Theorem number 1.5 says theorem number 1.4. Sorry, theorem 1.4. The statement of theorem 1.4 is the greatest common divisor Z of B and C can be characterized in the following two ways. First is it is the least positive value of Bx plus Cy where x and y belongs to the set of integers. So we have already saw that GCD is the least positive value. Mm, GCD is the least positive value of Bx plus Cy where x and y belongs to the set of integers. We have already saw that L is the least positive integer, and last we proved that G is equal to L is equal to B. So first part is already proved in theorem 1.3. Now we go to the second part. Second part says it is the positive common divisor of B and C that is divisible by every common divisor. Second part कहता है कि it is the second part says second part say it is the positive common divisor B and C it is divisible by every common divisor. Let D is the D is the common divisor of B and C. So this implies D divides B and D divides C. Since G is the GCD of B and C, there exists x naught comma y naught belongs to Z such that G is equal to Bx naught plus Cy naught by above theorem 1.3. Here we know that in the theorem 1.1 part C, D if D divides B and D divides C, this implies D divides Bx plus Cy for every integer x and y. Hence, since for every integer x and y, this implies D divides Bx naught plus Cy naught, where x naught and y naught also belongs to the set of integers. And from here, G is equal to Bx naught plus Cy naught. This implies D divides G, and the result is also and it is a positive common divisor of B and C that is divisible by every common divisor. So we take the any arbitrary common divisor like D, and G is the GCD, then it is divisible, then D divides G. So our theorem is going to be proved. Next, if an integer D is if an integer D is expressible in the form if an integer D is expressible in the form D is equal to Bx plus Cy, where D is not necessarily the GCD of B and C. This line says that if D is any integer and it is expressed in the form Bx plus Cy, then D is not necessarily the GCD of B and C. And we give the counter example of this line. However, it does follow from such an equation that B and C is the GCD of B and C is a divisor of GCD of B and C is a divisor of D. Take an counter example like 4 belongs to a set of integers, and 4 we can express 4 like 4 into 0 plus 2 into 2, where x is equal to 0 and x is equal to 0 and y is equal to 2. X is equal to 0 and y is equal to 2. it says that ki GCD of B and C, and GCD of B is equal to 4 and C is equal to 2. So GCD of 4 and 2 is equal to 2, and GCD of then 2 is the divisor of 4. मतलब 2 divides 4. This is the counter example. In particular कह रहा है कि if bx plus cy is equal to 1 for some integers x and y, then GCD of b and c is 1. If in particular if bx plus cy is equal to 1 for some integers x and y, then we can say GCD of then we must to say GCD of b and c is 1. Now we go to the next theorem, theorem number 1.5. The statement of this theorem says given any integers b1, b2, bn, not all 0, with greatest common divisor g, there exists x1, x2, xn, such that g is equal to GCD of this is equal to summation. Means theorem 1.5 is the general form general form of theorem 1.3. So we can prove similarly like this. We can take b1 b2 bn instead of b and c, and take the values of x1 x2 xn instead of x and y. And similarly we can prove this theorem. So theorem 1.5 can be proved similar to theorem 1.3. Now we go to the next theorem, theorem number 1.5. Theorem number 1.5 says for any positive integer m, GCD of ma and mb is equal to m into GCD of a and b. So we know in the theorem 1.4, GCD says GCD is the least positive values of max plus mby, where x and y belongs to where x and y where x where x and y belongs to set of integers. So we take the common values m, like m, and least positive values of x and y. And this is the definition of GCD of a and b. So m into GCD of a and b. So we also prove this theorem. Now we go to the next theorem, theorem number 1.7. The statement of this theorem says if D divides A and D divides B and D is positive, then GCD of A divides D, and DB divides D is equal to 1 by D and GCD of A and B. And if a GCD of A and B is equal to Z, then a GCD of A by Z and B by Z is equal to 1. I mean, this is the particular case of above. Matlab, this is the particular case of the above statement. So we in theorem 1.6, if we interchange if we interchange m if we interchange m by 1 by d and m eh, we if we interchange m we interchange m by 1 by d, then we have um, so we in theorem 1.6 obtained by replacing MAB in that theorem by D, A by A divides D and B divides D respectively. Then we proved this theorem. And इस particular को हम लोग प्रूव कर सकते हैं if we replace d if we replace d by z, then a by g into b by g is equal to 1 by g into gcd of a comma b. Since it is given that gcd of a and b is z by z is equal to 1. So gcd of a by z and b by z is equal to 1. Now we go to the next theorem. Theorem number 1.8. If GCD of A and M is equal and if GCD of A and M is equal to GCD of B and M is equal to 1, then GCD of AB and M is also 1. So we prove this theorem in XP pencilize. So theorem 1 point says if GCD of this is equal to 1, then GCD of AB and M is also 1. Now proof of this theorem. Proof of this theorem. Proof of this theorem. Let GCD of AB and M is equal to D, which is not equal to 1. I mean, let us assume GCD of this pen is so let GCD of AB and M is D, which is not equal to 1. Then, by the definition, there exists x, y belongs to set of integers z such that abx plus my is equal to d. Since D is the GCD of AB, AB and M, this implies D divides AB and D divides M. So by theorem 1.1 part 3rd, D divides D divides D divide the linear combination of AB and M. Linear combination of AB and X for any integer like AB X naught plus My naught for any integer for any integer X naught comma Y naught for any integer X naught and Y naught. Since it is given that since it is given that since it is given that GCD of M is equal to 1 is equal to GCD of B and M. So by definition, there exists x1, y1, x2, y2 belongs to set of integers such that by theorem 1.3 says ax1 plus my1 is equal to 1 and bx2 plus my2 is also 1. Now multiplies these equations. So we got ab x1 x2 plus am x1 y2 plus m b x2 y1 plus m square y1 y2 is equal to 1. AB x1 x2 V divides D AB x 0. This implies from here we can see D divides AB x 0 plus my 0 where x 0 and y 0 belongs to is any integer, x 0 is any integer. So D divides AB AB x1 x2 plus M A x1 y2 plus B x2 y1 plus M y1 y2. From here we put the values of this is 1. This implies D divides 1. D divides 1 implies that D is less than or equal to 1. Since D is less than 1, not possible because D is the GCD and we know that GCD is always greater than or equal to 1. This implies D is equal to 1. Hence, GCD of AB and M is equal to 1. Prove this theorem. Hence, prove. Now we go to the next theorem. Theorem number 1 point. Now here is a definition of relatively prime. Definition of relatively prime. We say that we